So in the last video, we constructed a 99% confidence interval for the mean weight of all bricks that come from a certain factory. That was the example we were doing. And the result of doing that was this interval right here. 2.210 and 2.301 are the endpoints of that interval, and we said with 99% confidence mu is in that interval. Now it's important to recognize interpreting this interval is a little bit tricky because you would like to say that there's a 99% probability that mu falls into this interval, but that's actually not true. Let me explain why. Because this interval that we derived from our sample, this is just a fixed interval of numbers, right? Its endpoints are just two numbers. So the question is, if you wanted to actually try and evaluate, so what is the probability that mu, this unknown parameter, is actually in this interval, 2.210 to 2.301? Well, what I want to point out is that that's not a question that can be answered in probability theory. And the reason why is because when we're doing this thing we're doing, frequentist statistics, this mu represents a number which I don't know anything about. It's not a random variable, it's just an unknown number. It doesn't have a distribution. What's the sample space? What's the distribution? None of these things are defined. So the probability that mu lands in this particular interval, that's not a question for the theory of probability, because we never quantified the uncertainty in mu. Mu is just a thing which may or may not land in this interval, okay? If you think about how we constructed this interval, so suppose I'm trying to evaluate the probability mu lands in a certain interval, all right? Now, if this interval is a fixed interval of numbers, one particular interval like that one, then this thing I'm finding the probability of, it's not an event in a sample space. It's just mu is a number, right, which I know nothing about, and I is a fixed interval. So it's like me asking you, what's the probability that Q is between 3 and 5? Then you ask me, okay, what's Q? I say, I don't know. Well, then you can't answer that question, okay? But the thing to remember is that this interval that we arrived at, what was it really? It was this. It was the interval x bar minus this margin of error and x bar plus this margin of error. That's how we actually calculated the interval. We took the mean of a sample and we subtracted and added the margin of error to it. And now in here you see, now this makes sense as a probability because I have a random variable, x bar. X bar is a random variable with a distribution. In fact, it's a normal distribution by the central limit theorem, assuming you satisfy the hypotheses of the central limit theorem. But this does make sense as a probability. So when we make a confidence interval, and you get this at the end, you have to be very careful to say it's not true. There's not a 99% probability that mu is in this interval. There's a 99% of probability of what? Of what? There's a 99% probability that mu, remember we derived this thing back here, there's a 99% probability of this inequality holding. But the thing that varies in this inequality is this x bar. This is the uncertainty in this inequality, right? Mu is just an unknown we know nothing about, but x bar is a random variable with a distribution. So the interpretation of this 99% confidence interval, it's not that after you make the interval, the probability mu lands in that interval is 99%. That's not true. What's true is that there is a 99% chance that when you take a random sample, you will get a random sample which results in a confidence interval that contains mu. Okay? So you can think of, we're sampling from some distribution. And when we take the mean of our sample, the central limit theorem tells us that those sample means, they come from a normal distribution whose mean is mu and whose standard deviation is sigma over root n. So when you take x bar, this x bar right here, the mean of your random sample, it's like drawing a number from this distribution. And let's suppose I do this a whole bunch of times. I take sample number 1, all right? Sample 1. I take the mean, and suppose I get this number right here. I'm going to write it like this. I'm going to put it right there. Then I take sample 2. I take a different random sample, which will have a different mean. Maybe I'll get this number right here. So I'm trying to indicate, I'm getting this number right there. You'll see why I'm drawing it down here in a sec. My first sample, I got this number right there as its mean. My second sample, I got this number right there as its mean. My third sample, let's say I get this number right, I don't know, here as its mean. My fourth sample, take a different sample, I get a different mean. Every time I take a different sample, I get a different mean. Maybe I'll get this guy. Okay, so I got these 4 sample means. Now, from each of these samples, sample 1, sample 2, sample 3, sample 4, I can make a confidence interval. If you look at the margin of error formula, you'll notice nowhere in that margin of error formula is there an x bar. It only depends on z star, which you derive just from this number 0.99 using the standard normal distribution. So it's going to be the same for all my samples. I'm going to come up with the same z star. Sigma is the standard deviation of the distribution I'm sampling from, and n is the sample size. So if I take 4 samples of the same size, each sample is going to have the same margin of error. So each of these confidence intervals I'm making is going to be the same width. So I'm going to be adding and subtracting the same number. So if I actually construct a confidence interval, all right, from a sample with this sample mean, I'll get a little interval. I'll get an open interval like this, say. So I'm going to represent this as the interval of numbers, on the axis right there. And from sample 2, I make a confidence interval. I'll get a different interval, but it'll be the same width. It'll be shifted around. From sample 3, I make a confidence interval. I'll get another confidence interval. Okay, I'll get another interval, same width. Sample 4, I get another interval from the same width. Now, if I look at mu, the mean of the distribution that I'm sampling from, then when I'm making a 99% confidence interval, I have a 99% probability that the sample I drew gives me an interval that contains mu. So in this case, this example here, 3 out of the 4, right? So 75% of these intervals actually contained mu. So if I'm doing a 99% confidence interval, if I repeatedly take samples again and again and again and again and again, and I make billions, millions, billions of these confidence intervals, one for each sample, then the 99% probability, the 90% confidence, it's a 99% probability of drawing a sample that gives me an interval that contains mu. So 99% of these confidence intervals I make will contain mu. But if I just take any single one, take any single sample, just take sample number 3 and ignore all the others. Just look at this interval. And I ask just this single interval, this fixed interval of numbers. What's the probability it contains mu? Well, it does contain mu. So there's a 100% probability it contains mu because it contains mu. So the point is that the uncertainty, the probability, it's from the process of taking a random sample. I'm not quantifying the uncertainty inherent in mu. Mu is just a number I don't know. It's not a random variable. But I am quantifying the uncertainty in the sample mean that I get when I take a random sample. And I'm doing that using the central limit theorem, because the central limit theorem tells me about the distribution of sample means when I take random samples. So this is a subtle point, but it's important to realize that that's the correct interpretation of this 99% confidence. So when you make a confidence interval, it's very important that at the end you don't state incorrectly, there's a 99% probability that mu falls into this interval. That's not true. The way you get away with it is you say, with 99% confidence, mu is in this interval. And when you say with 99% confidence, those are precise statistical words. And what they mean is that there is a 99% probability that the sample you selected gives an interval, that a random sample gives an interval which contains mu. Your random sample may or may not have been one that gives you an interval that contains mu. You don't know that because you don't know mu. But the point is the process you did of going from the mean of a random sample to a confidence interval over many iterations of taking random samples, 99% of the time, that process produces an interval that contains mu. Does this particular end result, is this particular thing true at the end? I don't know. But the process I used is a process that, when I use it on a random sample, 99% of the time, that random sample will be a random sample, which gives me an interval that contains mu.